Good Tuesday to you, everybody in Gov 603. Welcome to week kaboom 10. We have passed the halfway mark. A little tea for me this morning in my Route 66 cup because it's later in the day. It's about noon, and I am sufficiently caffeinated. Okay, welcome back. Did you have a restful modular week? I hope you did. All right, so we got a lot going on this week, but just a little for you in terms of your work. All right, so first things first, I have graded about halfway through the exams, your midterm exams. I expect that I will have them finished by Wednesday, tomorrow, and I have a separate video that I'm going to release. When I do that, and I'll talk about the exam and I'll walk through the questions and I'll point out some things that I think you need to pay attention to, and we'll take it from there. Okay. So, as I told you before you took it, the grade that you see when you took it is not your final grade because I have to grade the essay portion of the exam. Okay. So everybody just sit tight. Also during this week, I'll be grading weeks 1 through 8 of your discussion board, so you'll get a sense of where you are with that. So watch for those grades by the end of the week. I always grade them on the other side. I usually grade them during modular week, but this modular week I was out of the office and off helping family and away from work. Okay. All right. Let's focus our attention on this week's work. Okay. So at long last, you are going to get your eager little hands on some actual statistical work. I know you're chomping at the bit. And what you're going to learn how to do this week is a simple bivariate linear regression. So let's unpack those words, which should be very familiar to you by now. Okay. Simple meaning we're going to look at simple, some of the very fundamental outputs of the equation. I'll talk about that here in just a second. Bivariate. What does that word mean? Two, like bicycle, variables. Okay. So you can have multivariate regressions. And for the question, I'll give this one away. On the midterm, why ought we not to ascribe a single behavior, a single cause to someone's behaviors? Because people are complicated. Life's complicated, especially when you get into politics. Why groups behave the way they do is complicated. Now, what most political scientists and campaigners look for among multivariable causes of particular, behavior is what's the most significant, and they can focus on that. So in that respect, bivariate regression is useful to you. Okay, so simple bivariate regression. Okay, so simple meaning we're just going to look at some of the basic statistics. I'll talk about those in just a second. Bivariate meaning two variables. Regression. A regression analysis is the term that's used for causal analysis, meaning this is causing that. We want to see what the relationship is between this event and that event. So in the module for this week, I've got a couple of things for you. Number one, I have a reading it's titled "A Correlation versus Regression Made Easy: Which to Use and Why." So it's going to explain the difference between correlation, how you would conduct a statistical analysis of correlation, and of causation, which we term as regression. Why? I mean, how's a simple way to remember this? Regression meaning, when you think of regress, you think of something going down. Okay, well, maybe, think of something being pushed. This being pushed, or pushed back. Okay, so to keep it in your head. Okay, so read that selection. And then I have for you an exercise. All right, I have a sheet with a statistical table in it, and a little story about the relationship between severe COVID-19 outcomes and comorbidities. So let me explain that just a little bit. All right. Um, one of the I have a background in science, biology, anatomy, and physiology. That is how the body is structured and how it functions. And among a number of things, like where'd all the toilet paper go? One of the things that stuck out to me during the COVID-19 pandemic was how this virus was discussed, both in terms of the media and politically. And not all of it, not all of the discussion, be it strictly news media or used for political purposes, fell into the following category, but most of it, and that is, it was discussed as if this virus was something completely unknown to us. All right, that's factually untrue. All right, coronaviruses, and they get their name. Coronaviruses get their name. When you look at them under an electron microscope, you can't see a virus with a normal microscope. It's too small. And the reason that you can't see something with a normal microscope that's too small is the way that you see anything is that light has to go out, bounce off of that thing, like say this cup. Light has to come up, bounce off of that thing, and then come into your eye, and your eye registers it. So in this case, the light's coming from the screen of wherever you're watching this, and your eye is registering from it. All right. Well, light is made up of, it's a very interesting substance. It's made up of particles, but they travel in an energy wave-like formation. And that particle is called a photon, the smallest particle of light. So for you to be able to see anything, like I just picked up this container of Carmex, okay, for you to be able to see anything, a photon has to bounce off of it and then come back and come into your eye. I mean, millions of photons, but you get the point. Okay. Well, what if the thing that you need to bounce the photon needs to bounce off of is much, much smaller than a photon? Viruses are much smaller than a photon. So it would be sort of like, I'm just going to use this as an example. Let's say this was a particle of light. This Nalgene was a photon, and this was a virus. If you threw this at this would not bounce off of this. This would be moved, and you wouldn't. It has to bounce off and then go back to your eye. You would not see it. All right. Now there's a type of microscope that projects electrons, those thingies that are in the orbit of an atom, down. They bounce off of whatever the thing is, come back up to a sensor pad, and then that's interpreted as an image. That's an electron microscope. So back to coronaviruses. They get their name because when you look at them under an electron microscope, they're round like this, and they look like, if you've ever seen a picture of a solar eclipse, don't look at a solar eclipse, all right? But if you look at a picture of a solar eclipse in which you have this dark center, this is light, but you get the point. And then there are these little flames, all around the edge. That flaming edge, that fuzzy edge, is called the corona of a solar eclipse. Coronaviruses look like that under an electron microscope. They're darkish in the center, and then they have this light stuff that looks like it's emanating from it. All right. Coronaviruses have been around a long time. All right. And this one was named for the year that it first popped up, 2019. So one of the things that struck me interesting about the coverage, both media and political coverage, was that it treated COVID-19 as if we'd never seen a coronavirus before. And that's not true. Coronaviruses are all over the place. You get them probably every year, and they cause cold-like symptoms. They're respiratory viruses, as they infect the nose and the throat and the lungs, and they cause cold-like symptoms. It goes around every year. I mean, they're hardy little suckers. They've been around for millions of years, as best as we're able to tell, and they're not going anywhere. You're not going to mask coronaviruses away. You're not going to Clorox, bleach, sanitary, wipe them away. You're not going to vaccinate them away. They are proven survivors. They're tough little buggers. Okay. So that was one of the things that struck me, as if we'd never seen a coronavirus before. Well, the other thing that struck me, and this is where your assignment comes in, was the lack of discussion about what it is that we really should be concerned with COVID-19 infections. If we have it as a given, and it is, that you're gonna get viruses, they're just out there. They're very strange little entities. They're not alive in the sense of life, but they seek to reproduce themselves using your cells, and you're going to get viruses. So it's not a question of whether you will or won't get a virus. You will. I'm absolutely guarantee it. You have many, many times in the past, and you will many, many times in the future. But the question is, what's going to happen to you when you get the virus? Not if you get the virus, when you get the virus. And this was the other aspect of the coverage that struck me as strange, because there seemed to me, and I'm asking you in the discussion what it seemed like to you, that there was very little discussion about how it is that you reduce the severity of what happens to you when, not if, you get the virus. Because you're not going to avoid getting viruses. I mean, there's some viruses that they're just so, they're a particular type that we've not been able to develop a vaccine against them, or they one of the reasons is they mutate very, very quickly, and so we're trying every year. The flu virus is one of those, and a lot of those are coronaviruses, and we try to figure out which type of virus is going to be most prevalent during a given season, quickly develop a vaccine for that and get it out as quickly as possible. Most flu vaccines that you're getting, and I'm not suggesting that you do or don't take a flu vaccine. Don't get me getting this wrong. We're just dealing with statistics. Most flu vaccines that you get, at their very best, they are 50% effective, meaning at their very best, they're 50% ineffective. It's like a coin flip. Did the flu shot that you get, is this going to prepare your body as to what to do when you encounter this virus? In some years, they're even less. Their efficacy is like 25%, 75% ineffective. All right, that's just a statistical fact about vaccines. So viruses, very tough, very hard to run down. You're going to get them. The question is, what's going to happen to you when you get them? And how do you reduce the severity of what happens to you before you get them and when you get them? And that's where this exercise comes in. So what you're going to get to do, all right, I have for you a table, a data table, and a story, and then a link to a simple regression calculator. And this data table that you're going to see in there, and I think I don't know if you click on it or not, if you can get it larger, but if you're having trouble with the numbers, let me know and I'll throw up a link. But I don't think so. I think they're pretty clear. Okay. This table comes from a survey of data of 1.4 million people who were confirmed to have contracted COVID-19. And what the researchers did, and they did this by checking hospital records. All right. So this is quantitative research, although it's not survey research. All right, so one of the questions on the midterm is, what's the difference between qualitative and quantitative? And some of you struggled with that. We'll talk about that on Wednesday. So this is quantitative research using records. And what the researchers did is, of the 1.4 million people that the records that they surveyed, they looked at their age groups, right? They divided them into age groups. And then they divided them among age groups to comorbidities, right? What is a comorbidity? A comorbidity is a condition that you have before you have something else. All right. So let's say you have diabetes, right? That's a comorbidity. Okay. Or you could, you could have cancer and then you get another illness. The cancer is a comorbidity. Okay. So they took a look at the 4 most common comorbidities found in the populace. All right. And, the comorbidities that they looked at, the 4 that are most common, all right, are diabetes, cardiovascular disease, chronic lung disease, and kidney disease, which is caused by diabetes. It's sort of a full circle. So what you'll notice in that table is that each age group, starting from 0 years and going up to 80 plus years, is represented 3 times. The reason for that is that they took a look at the data of what was the outcome when someone got COVID-19 who had no comorbidities, 1 comorbidity, or 2 comorbidities. Now you might be asking, well, why did they only go up to 2 if they listed 4 comorbidities? Because the jump in severe outcome was so significant by the time they even got to 2 that they could see the trend. They just stopped. Said, okay, 2 or more, and the picture is dramatically changed. So what I want you to do to start this exercise, just look at the table. Look at the age groups, and it starts at 0 and it goes up to 17 years, and then it goes to 18 to 29 and 30 to 39. Find your age group, right? Where are you? Are you in the 18 to 29? And look at the 4 severe outcomes that they tracked. The first is people who got COVID-19 that ended up going to the hospital. Now, they may or may not have stayed in the hospital. We don't know, but it was bad enough that they went to a healthcare center. All right. And then of those that went to a healthcare center that were so sick that they had to be admitted to the ICU. That was the second, next severe in terms of what bad things can happen to you. Having to go to a hospital, maybe you stayed, maybe you got some fluids and they sent you on your way. Maybe they kept you overnight for observation. But when you showed up, you were bad enough that you had to be put in the intensive care unit. That's what ICU stand for. And then the next level up in terms of severe outcome was those that got put in the ICU had difficulty breathing on their own and were put on a ventilator. That is, had to have assisted breathing. And then finally, those that got COVID-19 showed up at a hospital, went to an ICU, were put on a ventilator, and then unfortunately died. All right, that's the severest of outcome from any disease is, well, death. So find your age group. So let's say it's 18 to 29, and look at the difference in percentages of people. And this is not the general populace. This is people who had COVID-19. Look at the difference in percentages of those that had no comorbidities, 1 comorbidity, and 2 comorbidities that say ended up in the hospital. So I'll just look at, looking together at this table, looking at 18 to 29. Those who had no comorbidities of the 4 listed, they may have had other issues, but they didn't have any of those 4. Okay, of everyone that had COVID, that were diagnosed, that were known, maybe they took a test, maybe they called into their doctor or whatever. 2.42% went to the hospital. Now, within statistics, remember the rule, the confidence interval rule, and that was one of the questions, that 95% and up, that's considered, statistically significant. So in other words, 5% or below, and it's not, if something happens, that's not considered statistically significant. So 2.4 is just about a little more than half of 5. So this was of no significance. That is, it's within, it's what's called the margin of error. So maybe they went to the hospital, maybe they didn't. All right. So if you were 18 to 29 and you got COVID, your chances of ending up in the hospital, if you had no comorbidities, were statistically speaking 0. But if you had 1 comorbidity, your chances of going to the hospital and being kept there went from 2.42 to 12.03. Now that is statistically significant because remember, anything above 5% with a 95% confidence interval, that's considered statistically significant. If you had 2 or more comorbidities and you were 18 to 29 and you got COVID-19 in this study, okay, your chances of ending up in the hospital go from 12.03 to 48.78%, almost half, 50-50. That's a significant jump. Now, the question is, and what we're going to look at this week is how much, what percent, okay, of the severe outcome was caused by the comorbidity. All right. And this is where you come in. I want you to spend a little bit of time. If you don't understand it, please get in touch with me. But before, like Sunday night, okay? Because this is due on Monday. Go to the link that I provided for you for this very simple stats generator. It's a simple linear regression calculator. All right. And it has a place for you to put in 2 variables. You can name them, and it's gonna plot them on an XY graph. Okay. So what I want you to do is I want you to pick an age range, and you're going to call that your explanatory X. So comorbidities for ages, you get to pick. Let's stick with 18 to 29. 0, 1, 2. Right? You'll see an example in the sheet. I think the age range I use is 40 to 49, but you get the picture. And then on the Y-axis, I want you to put the percentages, all right, of a particular severe outcome, and you pick, right? You want to look at the rate that they went on the ventilator. So you want to look at death. Do you want to look at what was the percentage if they landed in the ICU? So if you pick the 18 to 29, you'd list 0, 1, 2, okay, over in the X column. That's explanatory X. And then if you wanted to look at, say, you pick hospitalization rates, that would be your Y. So you would call it hospitalization rate. And you would enter the numbers 12.03, 2.42, 12.03, 48.78, because those would be the percentages of people that ended up in the hospital. Or what, if you don't want to pick hospital, pick death, pick ventilator rate, pick ICU, whatever you want. Okay. Then click the box that says include regression line, because you want to look at that. And then click calculate. And you're going to get a graph. You're going to get a line graph, all right, with a scatter plot, but you only have 3 data points on this plot. So, you're not going to get a lot of dots. And then you're going to get 2 values. You're going to get an R value and an R squared. Okay. Now, here's what I want you to do. This is your assignment. I want you to look up what does R in a simple linear regression represent? What does R squared represent? All right. And in both cases, what you're going to find, and I'll spoil it a little bit, is that the R and the R squared values tell you the percentage of how much of the outcome is being driven by the event. All right. So what you're looking for to say there's causation is high R and R squared numbers. And you're going to get them as decimals, and to convert them into percentages just times by 100. So in the example that I want you to take a look at, the example that I give on the sheet, and I think I use the age group 40 to 49. All right. But it doesn't matter which. You're going to see an R and an R square value, and then you're going to see a scatter plot with a regression line. Okay, so your task this week, go through the exercise, familiarize yourself with what R and R squared means. And you're going to get that in the material that in the readings that I've given you. Okay, run a simple linear regression, picking the age group that you want, 0 through 1 to 2 plus comorbidities, and then the severe outcome that interests you: hospitalization, ICU rate, ventilation rate, death, and put the percentages in there, and then run the calculation. Look at that scatter plot. Look at the regression line. The steeper the regression line going from left to right, the more significant the causation. And then look at the R and R square values. All right. And for the discussion this week, those are your questions. What does the R value represent? What does R square represent? What does your R and R square tell you about the causal relationship between a number of comorbidities within an age group and severe outcome? Okay. Does that make sense? That's your task. All right. So before you begin this exercise, read through the sheet carefully, and I've got a little story that goes with it as to why I'm using this. Read up and read the material on the difference between correlation and regression, and make sure that you're very clear on what R and R square stand for. What do they signify? What do they tell us about the relationship of this thing causing that thing? Okay, because we're never 100% certain, remember, because causal outcomes are complicated. Why did Van Gogh cut off his ear? It's not a single cause, but among all of the causes that we could look at, what we're looking at is the probability, the statistical probability that this thing is causing this thing, and then the statistical probability that the percentage of whatever the outcome is, this thing, is being caused, is being driven by this thing. Okay, that's what we're looking at for R and R squared. Okay, everybody, good luck. I hope you enjoy this exercise. Get your hands in there and actually get them on some real statistics. And this, if you can familiarize yourself with it, this regression calculator is a useful little tool, because then you can use it in your studies, and particularly in political science, when you can reduce outcome and output and input to two things. So if you want to look at how long the polls are open to percentage of people that vote, and you want to see, is there a causal relationship, and if so, how much of this is driving that, you can use this regression calculator. Okay, everybody, have a wonderful, wonderful week. I want you to focus on this. Come Wednesday, maybe after Wednesday, so I guess it'll be about Thursday, I'll talk to you about your exam, and then some other things we got for the semester. But for this week, stay focused on this. All right. Take care, everybody. If you need help, get me during my office hours. All right. I'll see you on Canvas. God bless.